Hello, my name is Diana Fisher. I am a retired mathematics teacher who taught system dynamics modeling as part of my high school mathematics courses for 20 years and also taught a high school system dynamics modeling course for 20 years. Peter Galbraith, my co-author, a person also very familiar with system dynamics modeling, and I had a conversation about the issue that no student teams were able to address the 2019 International Mathematical Modeling Challenge problem adequately. The IMMC is a team competition each year where teams of students have a 5-day window within which to address a given problem and compile and submit a modeling report subject to conditions designed to assure the authenticity of the work as the student's own. This is the 2019 IMMC problem. What is the Earth's carrying capacity for human life? Identify and analyze the major factors that you consider crucial to limiting the Earth's carrying capacity for human life under current conditions. Use mathematical modeling to determine the current carrying capacity of the Earth for human life under today's conditions and technology. What can mankind realistically do to raise the carrying capacity of the Earth for human life in perceived or anticipated future conditions? What would those conditions be? What made this such a difficult problem for students to address? It was a wicked problem. Wicked problems are hard to formulate, difficult or impossible to solve, can have multiple unintended consequences and multiple answers that are good or bad but not right or wrong. The 2019 IMMC problem was a great and important problem, but problems presented by spreading pandemics, economic recessions, environmental degradation, resettling of homeless people, require analysis defined by attention to interconnections, feedback, nonlinearity, and delays, meaning that simulation is required for solution purposes. And simulation was needed for the 2019 IMMC problem. It involved analyzing a complex system. Dr. Baryam, a complex system scientist, says to study complex systems, we have to develop an entirely new set of concepts that enable us to think about the behavior of the system. Really, most importantly, it changes the nature of the questions that we ask about the behavior of the system. It changes how we think. In this presentation, I will show you 3 simulation models that students could have built to start their solution to the 2019 IMMC problem. Each model runs from 1950 to 2150, 200 simulated years. Let's first look at the modeling icons so you will be able to understand each model representation. There are 4 icons that are used to create system dynamics models. Stocks, shown as a rectangle, represent those quantities that accumulate in the model and whose values we want to track over time, like population in a country, or money in a bank account, or global temperature. Flows, shown as pipes with 1 or 2 arrowheads, represent the rate at which the stock is changing value, or represent variables that directly increase or decrease the value of the stock. A birth flow could increase the value of a population stock if connected as an inflow. Converters, shown as independent circles, will usually hold constants. Connectors will specify the links between components. Stella is the preferred system dynamics modeling software for pre-college education. I used their free Stella Online software as a target environment for my pre-college model building. The free web-based Stella Online software allows a maximum of 3 stocks and a maximum of 20 icons for model simulations. I use this as a guide because it provides an opportunity for teachers to be able to use system dynamics models without additional expense in their classroom if their school has technology like laptops or tablets for students to use and a connection to the internet. For the first model, we want to decide how large a global population could grow if they only had grain as a food source. We will use grain production as a proxy for global food production because grain is a very basic global food source. Be aware that the following model would not be the first model students would build with system dynamics. They should have practiced some simple model building scenarios in their classes before working on a problem like this. Global grain production from 1950 to 2012 grew at a relatively constant rate. If we place a trend line on the data, we can get a reasonable equation that describes this growth. Observe the grain production in 1950. Observe the constant rate of growth shown in the equation. Using the data from our trend line, we place the starting 1950 grain production in the stock, 631 million tons, with production growing at 26.775 million tons per year. On the Macro Trends website, I found the data for global population and put a trend line on the time series data in Excel. For this model segment, I used the original population for 1950. Then I used the net growth fraction from the trend line. The stock flow model segment to capture world population growth starting in 1950 looks like this. Note that the flow first derivative is proportional to the stock value because it is calculated as a fraction of the stock value. So here are the two modeling segments that we have seen. We are interested in how long the food supply would continue to feed the growing global population. For that, we want to calculate the food each person would be allocated over time. The converter, food per person, would be calculated by a simple division of the two quantities upon which it depends. Here we see the food per person increasing over the first 50 years of the simulation, but decreasing after that. The food per person is pretty low in the last 50 years, but world population continues to grow without bound, which can't be right, so the model is incomplete. By the way, notice the thin pink line from 1950 to 2020 and the jagged thin orange line for food production from 1950 to 2012. These are historical data values from which our trend lines were developed. They are graphed on the same axes as the model output to see how well the model tracked the actual data at the beginning of the simulation. It would be helpful to know how much food, grain, a person would need to survive annually. So another converter is added to hold that information. It seems reasonable to think that when the calculated food per person falls below the minimum food per person needed each year, that dynamic should impact the change in population, slowing growth. So here we have added a new component called the effect of food per person on population. This component will be defined graphically, shown in the next slide, and you can tell it is defined graphically because it shows a tilde inside the circle. This effect component will send out a value that will reduce the population change amount per year. Let me explain. Here is the graph contained in the definition of the effect converter. On the horizontal axis, the current food per person is compared to the minimum food level per person. That fraction can be as low as 0, there's no food left per person, or as high as 2, there is twice the amount of food available per person than is needed. As the ratio is calculated each year of the simulation, a numeric value is output that gets sent to the flow and multiplied by the previous product, world population times net change fraction. If the ratio has a value of 1, then 0 is sent to the outflow and the population will not change. If the ratio has a value greater than or equal to 2, then 1 is sent out and the flow formula is not modified at all. But as the ratio moves from 2 towards 1, a value decreasing from 1 to 0 is sent to the flow, causing the flow value to become smaller and smaller. If the ratio is less than 1, then a negative value begins to be sent out to the flow, causing the flow to become negative and decreasing the population each year. As the ratio gets smaller and smaller, the impact of this negative value gets more pronounced. Executing the model at this point shows that we have controlled the population as desired, so it will not become too large that people will go hungry. It seems as if the problem is solved, but it still does not make sense. Food production cannot grow forever. There is the limitation of land availability for growing grain on a finite planet, and cropland will compete with land needed for people. So we need another fix. We need to add a production capacity to indicate there is only so much land available for food. We will add another graphically defined component to start to decrease the food growth amount per year if we are nearing production capacity. This model output makes more sense. The bottom graph shows the global population reaching a steady state as grain production reaches capacity. The top graph shows that this is a favorable outcome in that people have just enough food to eat. The global population in 2150 is 12.8 billion people. In the second model, we will consider population and how anthropogenic CO2 emissions impact global temperature. We will use the same data for global population segment, but we will have two flows in this segment. Births and deaths are separated. To design the temperature segment, I used data from NASA. I took the data and selected an exponential trend line. The population is growing exponentially, and we will use per capita CO2 emissions to influence the change in global temperature. So temperature should change exponentially due to CO2 emissions. I will use the 1950 global temperature, actually 13.8 instead of 13.83 degrees Celsius. And I will use the net temperature change fraction from the trendline equation. This slide shows the simple global temperature segment of the model using the 1950 global temperature and the net temperature change fraction from the previous trendline analysis. If the net temperature change value is positive, the biflow will act as an inflow and increase the value of the global temperature stock, as is the case here. The next step is to connect these two segments. I used a graphical converter to control how the ratio of global temperature compared to the global temperature in 1950 will alter or modify the death fraction of the global population. Next, I will show how I added calculations for per capita CO2 emissions to the model diagram. I decided to use CO2 per capita global emissions from 1950 to 2020 as an impact of global population on global temperature change, but the trend line did not fit the time series CO2 emission data well. Notice there is a significant drop in CO2 emissions in 1990. There is a New York Times article quoting a World Watch document suggesting that this decline was probably due to the collapse of the economies in 1990 of the USSR and countries in Eastern Europe that used significant coal to power their economies. So I decided to split the CO2 emissions trend line into two separate, very simple trend lines, one from 1950 to 1989 and the other from 1990 to 2020. These are the linear trendline equations for each set of data. I defined the per capita CO2 emission data using an if-then statement. The first trendline equation for emission from 1950 to 1989, and the second trendline equation for emissions from 1990 to 2020 and thereafter. Although if-then statements are frowned upon in system dynamics model, that definition seemed reasonable for this situation. The per capita emissions were then multiplied by the global population. The total CO2 emissions each year were then compared to the total CO2 emissions in 1950 in a graphical converter, and that information determined the impact of CO2 emissions on net change in global temperature. This graph contains the global population, green, and the global temperature, red, graphs from 1950 to 2150 produced by the model. The light orange graph from 1950 to 2020 is the historical global population, and the jagged purple graph is the historical global temperature from 1950 to 2020. Also on this grid, we see the United Nations global population projections for 2050 and 2100, and the Intergovernmental Panel on Climate Change projection for global temperature for 2040. The model captures these projections well. The shape of the graphical converters allowed me to capture these projected values reasonably well. Here, the maximum population is reached in 2095 at 11 billion, but decreases after that to 11.4 billion in 2150 and continues to decline. The third and final model deals with global population and global potable water consumption. The global population segment is the same as for the previous model. In the potable water segment, we have one stock identified as easily accessible potable water. It is increased by regeneration and decreased by consumption. On the consumption side, the global population is consuming the water. The total consumption for 1950 was found on our World in Data website. It represents a human water consumption and potable water used for industrial and agricultural purposes. That value was divided by the global population in 1950 to produce the 484 cubic meters of water consumed per capita. The regeneration fraction was a guess. This value produced either steady state or slightly increasing easily accessible potable water stock values from 1950 to about 1980. The initial stock value came from the U.S. Bureau of Reclamations in California. Global population is connected to water consumption. In this, a per capita water stress level below which normal daily living becomes negatively impacted is part of the model. This value includes both human water consumption and needed agricultural and industrial water to support a person. The current easily accessible potable water level is compared to the total population water stress level in this graphical converter. Based on that ratio, a multiplier is sent to the actual death fraction to change the death fraction based on the impact of the amount of easily accessible potable water that is available. The total population water stress level also impacts how much water people can consume. Less water means less consumption. Moreover, the consumption of potable water per capita has increased by 1.8% each year for the last 100 years. So water consumption outflow is a super exponential process, which does not bode well for humans on this planet. This slide shows business as usual model output. The blue graph shows the global quantity of easily accessible potable water. The dashed brown graph shows the total water consumption outflow per year. Water has a significant impact on the size of the human population that can be supported. This business as usual graph has a maximum global population occurring in 2060 at 10 billion people, but global population in 2150 is 8.2 billion people and falling. Students can combine these smaller model scenarios as modules of a larger model, so the 2019 IMMC problem could be addressed more realistically using this approach. High school students have shown for 2 decades that they can build and explain models much larger than those shown in this presentation. Thank you.